So far we have seen unsigned numbers and their representations, right? We can use decimal, octal, hexadecimal, everything. But generally we prefer binary representations because your computer is designed such a way that it can understand binary numbers clearly. Okay, right. But the problem is we have not discussed how to represent negative numbers, isn't it? So that's why we have to talk about how to represent sign numbers. Sign numbers means positive, negative, both. Okay. For that we use sign magnitude, ones complement, twos complement representations. Okay. Now let me bring our computer into the picture because so this entire story, whatever we are studying, it's only because of this computer, right? Now we'll ask, my dear computer, so can you understand, integers? Yes, I can understand. But how do we know that, let's say, this computer understands that these binary patterns are integers? Very simple. So the computer is nothing but circuits, right? So if you give integer 2, integer 3 using some format, I don't know. Okay, we'll discuss that. Somehow if you give 2 and 3 to this computer and if you ask that computer to do addition, then the output is 5. Okay, that means of course again in the same format what we are assuming, that means some format is given as output, but we know that that is, let's say, representing 5. Whenever you give 2 and 3, if output is 5, then we say that your computer is understanding integers. That's why it was able to add them properly. That's it. So this is about your computer understanding numbers, right? Now the second thing is this computer is going to take the data integers and it is going to add them, otherwise subtract, multiplication. To perform the operations, then it is going to have circuitry. When it is having example, let's say adder circuit, then this adder is designed such a way that it takes inputs and that input is nothing but integers and your adder will be designed like this. Okay, so data will be taken through registers. We will see that details later. So in the registers we are going to store the data. That's why we have to fix the size of the integer. If you have very large integers which cannot fit in these registers, then this adder cannot perform this addition function, isn't it? That's why we have to fix in computer. What is fixed is integer size is fixed. So now let's come to our concept. When you have signed numbers and we are going to represent them for this computer, then this computer will fix the size of the otherwise number of bits in that integer. Okay, since we are going to use binary patterns only, then with that n bits, how many binary patterns we can generate? 2 to the power of n. Okay, remember it. So I am assuming that, let's say, your computer now supporting n bit integers because it can take n bit integers and it can do manipulation. Then how many binary patterns we can generate? 2 to the power of n. Now let's begin the story. First thing, signed magnitude representation. In signed magnitude representation, for simplicity, first of all I assume that, let's say, I am going to represent only using 4 bits. Okay, 4 bits, 1 2 3 4. Then how many patterns can be generated? 0 0 0 0, 0 0 0 1, 0 0 1 0, 0 0 1 1, then 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 triple 1, then 1 followed by triple 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1, correct? So everywhere 1. 4 plus 4, 8, 8. 16 patterns can be generated. Now since we have to represent negative numbers, so all the patterns which starts with 0 are given as, otherwise fixed as positive numbers. This all the patterns which starts with 1 can be assumed as negative numbers. So this is the concept in signed magnitude representation. Okay, so now the interesting thing, if you see, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. Now here this is minus, this will be value. Okay, so 0 0 0 is value 0, minus 1 represents negative number, 0 0 1 means 1, in that way, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. So this is about signed magnitude representation and their numbers. But if you see, one drawback I can say, 0 has 2 representations. Whenever there are multiple representations, so we will be wasting one representation, one thing. Second one, so there will be ambiguity. So because of this ambiguity, what happens is, so 2 representation for 0, right? Example, let's say in your computer, so your processor is comparing one variable x with whether it is checking like this, x is 0 or not. Now this x can have two patterns, right? Maybe all zeros, otherwise 1 followed by all zeros. Then your circuitry should be designed such a way that it should check two times. First of all, it should check like this. Is it all zeros? Second, is it 1 followed by 0, 0, 0? In any case, it is going to be 0. Correct. So I can say that rather than one comparison, here you require two comparison. So it may take more time, right? In that way. So because we are going to study computer organization with what motivation? With optimization motivation. Correct. We have to optimize everything whenever it is possible. That's why if we have a chance, we have to avoid it. That's why in sign magnitude representation, that is treated as drawback. Okay. So one of the drawback is having two representations. Second thing, doing manipulations, like generally when you have numbers, what you do? We do addition, subtraction, multiplication, right? When you have sign magnitude representation, then addition, subtraction will be little bit difficult than other representations. Okay, we'll see the reason why it is little bit difficult here. So example, let's say you have one number which is positive number 0001 and you have a negative number something 1 followed by 11110. Example, let's say you are doing addition. Okay, take the second case 0101 0110. If they are positive numbers, then if you know that they are positive, then addition will be very easy. Add these two bits, we can have adder, right? So we will be studying full adder and half adder, don't worry. So using that I can add these two bits, then I get 1, then after that 011, again adder I use here in that way. So 1 plus 1 0, here carry will be 1, that carry will be propagated to this one. So in that way finally we can do the addition, not a problem, without seeing the sign bits. If you know that these two are positive numbers, this will be the addition. What if one is positive, one is negative? Then blindly adding them, will it work? We'll see. 1 1 1 1. Okay, so 1 plus, what is this representation? Plus 1, right? This is minus this 6, correct? Minus 6 plus 1 is minus 5, but it is not minus 5. That means we have to change the addition model. Okay, fine, we will change, not a problem. But first of all, we have to see these two bits, right? So based on whether they are positive or negative, we have to decide the circuitry, correct? That's why it is little bit complex. It's not straightforward, finally I want to say. Okay, it's not straightforward. So that's why sign magnitude representation is not used nowadays. Okay, remember it. So implementation is difficult because addition, subtraction will become little bit costly, otherwise I can say lengthier. Okay, they take little bit more time than here 1 in 1's complement, 2's complement. You will understand that after studying 2's complement. Remember it now. Second thing is 0 has multiple representations. Now one interesting mathematical question here is, example, let's say you have n bits. What is the range of numbers you can represent with that n bits in using sign magnitude representation? First bit is definitely going to be for sign bit, correct? So if it is 0, then how many other positions you have? N minus 1. So if it is 1, then it will be all negative numbers, then again n minus 1 positions. So with n minus 1 positions, how many patterns we can generate? 2 to the power of n minus 1. So here also with 1, 2 to the power of n minus 1 other patterns, correct? Because there are n minus 1 other positions. So what I want to say is, finally you have 2 to the power of n minus 1 plus 2 to the power of n minus 1, which is nothing but 2 to the power of n patterns. But out of them, 0 is using 2 patterns. That's why the number of numbers which are going to be represented, that means total distinct numbers which are going to be represented is 2 to the power of n minus 1, because 0 is taking multiple numbers. Second one, we will see the range. The range is like this. You are going to represent 0, isn't it? Yes. In the negative, what is the least number? Minus 7 for 4 bits. So to know the value, these last 3 bits are important, right? So with last 3 bits we can represent maximum 7. That's why least number can be represented minus 7. Similarly, when you have n positions, apart from the first bit, remaining n minus 1, with remaining n minus 1 positions, what is the highest number you can write? What is the highest number we can write? 2 to the power of n minus 1 minus 1, correct? And especially that is a negative number. So that's why it is the smallest. Up to maximum 0111. That means 2 to the power of n minus 1, n minus 1 minus 1. Okay. So this is the answer. You just check it out. If n is 4, it would be minus 2 to the power of 4 minus 1. 4 minus 1 is 3. 2 cube, 8. 8 minus 1, 7. 2 2 to the power of 4 minus 1 2 cube, 2 cube minus 1 7, minus 7 to 7. This is a range of numbers which are going to be represented. The total number of patterns we are going to represent only 2 power n minus 1. Of course you have 2 power n patterns, right? Remember it.